Okay, so I guess Anders' first speaker was microphone. Doesn't work. Can you hear me well?
Yes.
Okay. So I guess the first speaker was a former ASA student. So first day ASA. And I guess many of the former speakers raised ASA as a very important scientific impact, which is usually measured by an H factor. I would like to present a new scientific metric, which is the student factor, okay? Which I define as the number of PhD students who end up being professors divided by the number of PhD students, and it's next for ASA, it's approaching unity, okay? Okay, so that's
ASA ratio.
The ASA ratio, okay? And, okay.
Exactly what?
I think the asymptotics is what I hope for. Okay, and this is of course not by chance. So ASA is really a student-oriented advisor, and it's been a really inspiring experience. Spend my PhD being advised by ASA. Okay? Okay, so let's go to the physics. So I will tell you what happens to the confinement transition of the Ising lattice gate theory when it is coupled to fermions. So this work has been done in collaboration with Mohit, with here, and also with Asher. Okay, so just to set up the problem, let me try to give you general motivation before I go to details. So I guess just reading my talk's title, you might have thought this is kind of a high-energy talk, but it turns out that gate theories play a very important role also in condensed matter physics, where unlike the high-energy case, where the gauge bosons are actual elementary particles which mediate the interaction between matter fields, in condensed matter theories are typically emergent, and they play a very important role in describing different spin-liquid state, diffraction Hall effect, and even there was some suggestion that it might be relevant for high-energy materials. So there is a fundamental problem, at least in trying to tackle such problems numerically, which is that at finite fermion density, okay, those models suffer from the numerical sign problem, and as we learned from the previous talk, it doesn't make any sense to try to perform any quantum Monte Carlo simulation in the presence of a sign problem. And so what I show you today is a very simple model of a lattice gate theory, okay, which we found that it's free of the numerical sign problem, even in finite fermion density, okay. And so this allowed us to perform an unbiased quantum Monte Carlo simulation, and we found a very rich phase diagram, okay, which exhibits BCS to BC crossover and even an emergent Dirac physics.
And you are not using us loosely?
Yeah, it's done. Okay. So, okay, so just to set up the problem, let me quickly review the physics of the Ising lattice gate theory and the confinement transition. So, we'll consider a square lattice, and the degrees of freedom are, okay, it used to be red arrows, but I guess it's orange arrows, are Ising spins that live on the bonds. And the Hamiltonian consists out of two terms, a magnetic flux term, okay, which essentially measures the magnetic flux threading each plaquette. And essentially, because we have binary degrees of freedom, this can be either 0 or pi. And we have a competing transverse field term, which favors aligning all the spins in the positive x direction. So it's not sufficient to specify the Hamiltonian there to fully capture the theory. We also need to project to the physical Hilbert space. And this is done by an Ising version of the Gauss law, okay? Which in simple terms is just the product of the sigma x operator over all bonds emanating from a specific site, and this must equal unity. Okay? It means that we have no Z2 charges. Just to make this more visual, so here we have two spins pointing in the positive x direction, so this is a kosher state. And in a state where we have an odd number of spins pointing in the positive x direction is outside of the physical Hilbert space, and we must project it out. So those two terms would compete, Okay, and we do to a quantum phase transition. So let's see how it goes. So for very large values of h, okay, the ground state is the product state, where all the spins point to the positive x direction. In order to understand why this is a confining state, so let's imagine now that we introduce two Z2 charges. So in order to satisfy the constraint, we'd have to generate a string which would connect them. The energy cost is h per bond. And this means that the energy cost of separating the two Z2 charges goes linearly with the separation. Okay, so this means that we have confinement. Of course, this would get renormalized by quantum corrections. And eventually, as we approach the critical point, the string tension would vanish critically. Okay, following this power law. Here, nu is, as we learned from the previous topic, the correlation length exponent, and the critical theory here is relativistic. So the dynamical exponent is 1. And eventually, the string tension would vanish and would deconfine. And deep in the deconfining phase, the ground state is a state in which the flux switch plaquette vanishes. It's exactly 0. And we'll get quantum corrections as before. And the lowest order question is a single spin flip will generate 2 pi fluxes, known Anna Fisher as a Vison. The Vison energy would also vanish near the critical point, and one can also understand these critical theory as a condensation of those Vison excitations. Okay? I would like to make 2 comments here. First of all, this transition does not involve any symmetry breaking, because a gauge symmetry, a local gauge symmetry cannot be broken according to Litsu's theorem. And the second important piece of information is that this critical point can be exactly mapped to the 3D classical Ising model, and hence they share the same universality. Okay? So now let's see how do we couple this theory to fermions. Okay, so let's imagine that the fermions live on the sides of the square lattice, and they can hop. And the way that we couple them to the gauge field is by minimal coupling, which in this case, it amounts to an Ising version of the pilot substitution. Okay? And more explicitly, this can be understood as follows. So the hopping amplitude, okay, more specifically, the sign of the hopping amplitude is determined by the Ising gauge field along the bond. In addition, we need to modify the Ising-Gauss law, because now we have dynamical gauge fields, so they play a role. And it's important to notice that the gauge field is only sensitive to the parity of the fermions. Okay, it doesn't care about the actual Fermi number, it only cares about the parity. So we have -1 to the number of fermions. And the main question we'll try to answer is how do the fermions affect this transition? Okay? Okay, so let's try to now consider a few limiting cases, okay, to try to sketch a general structure of the phase diagram. Okay, so first I will consider the case where the chemical potential is non-vanishing. I will show you that a lot of interesting stuff actually happens when the chemical potential is 0. So first let's look what happens deep in the confining phase. Okay? So here, in order to satisfy the constraint, the fermions must form fermionic molecules, okay, which consists out of a spin down and spin up fermion. Okay? So of course, again, we have quantum corrections which would delocalize those molecules, and a nice way to see it is by using the following virtual process, where we first break the pair, okay, and generate a string connecting them with an energy cost of h, and then we'll recombine fermionic molecule. Okay? And now you can see that the effective hopping, following second order perturbation theory, goes like t squared over h. And now those fermionic molecules, of course, are bosons, and at low enough temperatures, they would eventually condense and form a BEC state. Okay? So now let's look what happens in the deconfined phase. So here the fermions are free, and they would start filling up the cosine band and form a large Fermi surface. But one can show that they still have a very weak and local attractive interaction, and will inevitably have a BCS instability, okay, which will lead to a BCS state. Now I'd like to make 2 comments. First, the fermions have gaps throughout this transition. They have a superconducting gap. And therefore, essentially, they can be integrated out, and they are not expected to change the critical properties of the underlying Ising gauge field transition. So it's expected to stay in the same universality class. But I would like to contrast this transition to the usual BCS to BC transition, because here we have an actual singularity in the attractive interaction at the critical point, unlike the usual BCS to BC scenario, where the strength of the attractive interaction is just very smooth. Okay, so now let's see how it looks like in the numerics. But before I do that, I would like to explain why we don't have a sign problem, and now we enforce the constraint, because actually it involves some technological novelty in order to do that. So let's start, as usual, with our partition function. So unlike the usual case where we just trace over the thermal density matrix, here we need to project to the physical Hilbert space. So we need to figure out a way to incorporate this constraint in the numerics. So there's a nice way to do that. We exponentiate the constraint by using a discrete Lagrange multiplier. And physically, this Lagrange multiplier, which I call lambda sub r, can be mapped, if we make the connection to quantum electrodynamics, to the temporal gauge field, A0. And now we just, okay, we can do the usual quantum to classical mapping and evaluate all the matrix elements and write down an imaginary time path integral, which consists out of two terms. So the first term here is just a bosonic action, which is essentially the usual three-dimensional classical Ising gauge theory. And those two terms are the fermionic determinants. Okay, we have one for spin up and spin down. And the crucial point that I'm skipping the technical details, but they explicitly depend on the temporal gauge field. Okay? So now, in order to see why we do not suffer from the sign problem, so the two determinants are real, okay? And the spin up and spin down determinants are equal. So this means that the square root is strictly non-negative number. Okay, so this means that we avoided the sign problem. So I would like to stress a few points. So first of all, it doesn't work for U1 gauge symmetry or any larger gauge symmetry. And the reason is that the determinant would be complex and it wouldn't help us to square it in order to get a non-negative number. And the second point, that more generally we can simulate any even number of labels. Okay, in our case we only take n equal 2. Okay, but in principle it could be a larger number of flavors. And the final point that we managed to enforce the constraint using our temporal gauge. Okay, so let's see what we see in the numerics. So first we'll study the Ising sector. So our main tool would be the average magnetic flux. Okay, we don't have a natural order parameter because it's a gauge theory. So we probe the average magnetic flux. So here I'm plotting the average magnetic flux as a function of the transverse magnetic field. Each one of the curves corresponds to different system size. So first let's look even the deconfining phase. So here, H is much smaller than J. We expect a zero flux phase, meaning that the expectation value of B goes to 1, symptotically. And in the confined phase, where H is much larger than J, B should go to 0. Okay, all of the energy would be stored in the electric field instead of the magnetic field. And you see that also it develops some kind of a singularity here, which can be plotted by looking at the susceptibility. And we see a peak at the susceptibility, which finds the location of the critical point roughly at 0.56. So let's see what the fermions do. So the first pole would be the superfluid stiffness, okay, which, as we learned yesterday, measures the Meissner effect. And you see that the superfluid stiffness, although it drops at the critical point, it remains finite throughout the transition. So this means that we are fully superconducting throughout the transition. So it fits the scenario of BCS to BEC. And most importantly, here on this straight blue line, give us the jump of the superfluid stiffness at the KT transition. So we above it. So it means that this result is not due to some thermal fluctuations. And as another point, we can look at the S wave pairing superconducting order parameter, which also remains finite throughout the transition. So indeed, this fits our scenario of a BCS to BEC transition. So now let's.
In order to the question, why is the superfluid density higher on the BEC side?
Yeah, it's a good question. I'm not sure if it's some fundamental reason or it might be something with specific microscopic parameters, but yeah, we'd have to think about it. Out of the top of my head, I don't know. I can give you an estimate for the superfluid stiffness deep in the confining phase. It should go like T squared over H. But for the BCS, okay, it's hard to estimate the strength of the attractive interaction. So it would be hard to estimate also the superfluid stiffness. But there might be an easy way to see. I don't know.
What is the temperature there?
Here. So it's okay. It's just a number, but it's 32. But
PPDCS.
so okay. So maybe I'll show you comparing this to the KT transition, where it's the relevant temperature scale. Okay, in the next slide. Okay. So in order to make the connection to BCS to BC, we yeah, of course, yeah.
Did you look at the fermion-Green function and make gauge invariant and some suitable variant?
So first of all, it's not gauge invariant. You can make it, okay, but then it's a gauge choice. So yeah.
What does he do with the sort of natural straight line?
We haven't looked at this, but I guess we would have to make a smart gauge choice in order to get sensible results that you can
Or
interpret.
even just the gap. But then, then your gauge choice should still be running with the actual string along the time direction. But I guess I was wondering how small or large is the fermion gap at your transition?
It's very hard to distill the fermionic gap. So everything is mixed in. You would have to write down some gauge invariant correlation function which would have a gap. So the fermions and the gauge field are mixed. There's no way to really tell what is the fermion gap, what's the gauge field gap. It's not. Yeah. Okay, so let's make a connection to the KT transition. So the most straightforward way to do that is to estimate the KT transition with the intersection of the Nelson-Kosterlitz jump at the critical point. And we see that similar to BCS, we get some sort of a dome shape, which is maximal on H equal 1, and here is the critical point of the BCS, of the confinement transition. So now let's move on to the zero chemical potential case, okay? And we have in our disposal another energy scale, the Hoping amplitude of the fermions, okay? So let's see what happens when we look at the large Hoping amplitude limit, and this was worked out also by NASA. So essentially we need to minimize the kinetic energy of the fermions, okay? So we have the following problem. Find the gauge field configuration which would minimize the kinetic energy of the fermions, okay? So it turns out, it seemed like a trivial problem, which you might have guessed that maybe, you know, a uniform gauge field where all the sigmas equal 1 would give you the lowest energy, but it turns out it has a non-trivial answer, which is a pi flux phase. Okay? So a pi flux phase minimizes the kinetic energy of the fermions, and this has a very drastic consequence on the dispersion relations of the fermions. Because now we would have 2 Dirac nodes, okay, per spin species, okay, and the low energy physics would be gapless. Okay? And so this leads to a very interesting possible scenario. So let's say we start from the confining phase. Okay? And now we increase the strength of the Hoping amplitude. Okay? So we can move to a deconfining phase with Dirac fermions instead of a BCS state. Okay? And now we would like to first ask the question, is it a direct transition? There's another possible scenario. There's some intervening deconfined superconducting phase. We can maybe gap out the fermions before we move to a confinement. And if it's not the case, and if this happens at exactly the same point, it means that the fermions are gapless at criticality. Okay, so they play an active role in the low energy physics, and this is some kind of a new universality, possible new universality. Okay. And so, so this is our sketch for our possible exotic phase diagram. So we have a BCS to BEC transition, which is a confinement to deconfinement. And as we increase the Hoping amplitude, we might end up in a deconfined drug phase where the Dirac physics is emergent. We didn't start from a relativistic theory, but we have an emergent low energy relativistic theory. So it turns out there's another, maybe more direct way to encode those pi fluxes, and this is by picking the negative value of J. So in this case, in the deconfined phase, the ground state is a pi flux phase because we, by hand, put an energy cost for a zero flux. We would like to have a pi flux phase. So in this case, the transition would be follows. We start from a deconfined Dirac phase for low values of the transverse magnetic field and end up in a confining BEC phase. Okay? So let's see what the numerics tells us. But before we do that, it turns out that although we eliminated the sign problem, we have a zero problem. Okay? And which is made more difficult than the sign problem. So let's see how it goes. So at zero chemical potential, we have, okay, it's not emergent, it's a particle symmetry. And let's see what happens if we act with particle symmetry only on one spin flavor. In this case, let's take the spin down, of course, without loss of generality. The same thing applies for spin up. So the determinant transforms non-trivially under this particle symmetry. And we get an additional Berry-phase contribution, which is the product over the temporal gauge field. Okay, this is a gauge invalid quantity. It's okay. And now in the odd sector, meaning that this product equals -1, and we see that the determinant equals its minus, and hence it must vanish. Okay? So there's another slightly, okay, it's okay way, but slightly more, okay, maybe nicer way to understand this. So the temporal gauge field acts as some sort of a complex chemical potential, and we know, well, essentially we cannot get zero modes at finite temperature of fermions because the lowest Matsubara frequency sits at pi. Okay, it doesn't sit at zero. So what the gauge field does, it shifts the Matsubara frequency from pi to 0 and enables us to form a zero mode. Okay? So naively this seems like we don't have any problem, it just means that we don't sample the odd sector. Okay, it has a zero probability. But it turns out that this creates a systematic bias because some of the observables are not symmetric under particle symmetry of a single species. Okay? So in order to solve this, we eliminate the zero mode. You always use SVD eventually, somehow. So we eliminate the zero mode using a singular value decomposition and sample from an extended configuration space. So I'm skipping the technical details, but just to show graphically why it is important. So the red curve here is exactly analyzation result. Okay, this is the exact result. And the green curve is just the contribution of the even sector. So you see that it's completely off. And until we add the odd sector contribution, here in the blue curve, you see here. So the two curves fall right on top of each other, and the odd sector contribution exactly compensates on our missing rate. Okay, so it's really important to add the contribution of the odd sector. Okay, so let's move to the actual numerical results. So first we look at the pi flux phase generated by taking the negative value of J. Okay? So as before, we look at the expectation value of the magnetic field. So now deep in the deconfined phase, where H is much smaller than J, here we see that the expectation value of the magnetic field tends to -1, meaning that we form the pi flux phase. Okay? And as we increase J, we go to a confining phase, and as before, we develop some kind of singularity here. And if we look at the susceptibility, we get a peak, which corresponds to the confinement-deconfinement phase transition. So now let's look what the fermions do. So first, let's look at the S-wave fermion amplitude, which would act as an order parameter for the superconducting state. So we see that in the deconfined phase, it slowly goes to 0. Okay? And this means that we are in a Dirac phase, because a Dirac fermion, unlike a full Fermi surface, does not have a BCS instability. And we get a non-superconducting state, and as we increase stage, we go to a BEC state. So we have a superconducting phase transition. And the interesting point, or the crucial point here, is that it happens exactly at the same point. So confinement, deconfinement happens exactly at the same point that we have the superconducting ordering transition. So this hints us that it is possible that we have some kind of a new critic point with a new universality class. So in order to check this, we perform some scaling analysis as we learned from the previous talk, it's always good to write down some sort of a universal amplitude, okay, something with a zero scaling dimension. And we will use the superfluid stiffness. So superfluid stiffness slowly goes to zero in the Dirac phase and gets a finite value in the BC phase. And now in 2 dimensions, if you look at the product of L times rho s, it's a universal amplitude, and we can write that as a scaling function. And we see a pretty good curve collapse with the following critical exponent. And this also serves as a check for the Dirac phase. Okay? So, so one can compute this product, L times rho s, deep in the deconfined phase, where we expect to see 4 free Dirac fermions. And this value should be pi over 2, and we see that asymptotically we approach this value. So this is a very nice probe to detect Dirac physics. And finally, I would like to try to see if we get an emergent Dirac fermion as we increase the popping amplitude. So again, I'm plotting the expectation value of the magnetic field. And I would like to mention that J here is positive. So essentially, we expect to see, we would favor seeing a zero flux phase. So let's increase the strength of the popping, okay? And we see that the expectation value of the magnetic field tends to -1. So the fermions locked the gauge field to a pi flux phase. Okay, this is an emergent pi flux phase. We didn't put it by hand. And also we can look at the stability, and we see a peak here. This is a confinement deconfined phase condition. And also, as before, the fermions themselves go from a PEC state, where they condense, to a Dirac state where the fermion amplitude vanishes. Okay? Now, just to summarize, so I've presented a lattice gauge theory, which is free of the sign problem even at finite fermion density. And it exhibits a crossover between a BCS to BEC transition, BCS to BEC phase driven by confinement. At zero chemical potential and at large popping altitude, we get an emergent Dirac fermion. And we believe we found a universal class of the Ising lattice gauge. Thank you very much.
Superfluid density, you measured in the transverse field.
Yeah.
So why would you get anything zero in the Dirac phase?
It's zero, but it scales like 1 over L. So,
I don't know.
yeah. And as L goes to infinity.
So what was this pi thing? That was L times.
L time. So, okay, it's okay. So essentially, this is all of this phase is a critical phase. It's like the critical point between a superfluid to an insulet. Okay. So if you look at L times rho, it's finite. Okay, but as
What about if you ever look at the susceptibility of, Matthew was asking about a gap, you look, the engagement variability for a gap, but
yeah, that's okay. So I guess most of the observables I've shown here were like thermodynamic observables, and we can definitely look at dynamical observables. The gap.
No, the spaces.
The spaces. Okay. I haven't looked at this.
I have a question. So, and then completely follow you. We talked about the light in the odd sector.
Yes.
Is it clear that this is not an actual physical bias because you have a shift in the complex shift in chemical potential is free?
Okay.
Why doesn't it? Yeah. I mean, why don't you see it in the exact representation? Why is it something you need to complex?
Okay, so the key point is that for a given configuration, the weight of the partition function can vanish. Okay, and this means that you don't sample this configuration. Probability is 0. But when you want to compute an observable, you need to put an operator here. And by doesn't mean that the trace over this operator would vanish. Okay, so that's the main difference. So the weight of the partition vanishes, but not the overlap, the projection to a specific operator does not have to vanish. So you miss some of the weight.
On the same slide, I was a bit confused at how you implement the constraint. Yeah, so let's see. So is that top line a constraint? Is there a constraint there or no?
Okay, for the gate theory, the constraint is essentially is the spatio-temporal of your book, not the spatio-temporal plaquette. Okay, but in the terminal it's slightly more complicated. So I can show the explicit expression, but it can be done.
XP is purely real.
This is real, and this one is also real. It's a change of the fermionic determinant. So there's some details of the algebra.
Yeah, I was confused by the rotation.
I'm sorry.
A silly question. Is there any experimental realization of the model?
This is the question I fear the most.
There was an experiment.
I can send you to Fisher incentives paper.
No, but some combination, I think, some combination of superconductors and magnets, even a imaginary.
Okay, so maybe one. Okay, if there was a spin liquid, okay, that was a Z2 got a spin liquid, so you might think of a transition over there. But,
Alright, well, since it's you and I can't resist, so forthcoming paper with errors and Munich where is a slight extension of this model which applies, we think, to spin density wave transitions in various matters, including the type that you studied.
It's not out there yet, the paper.